Alright, this is the section 8.6 online trig notes, double angle and half angle formulas. In the previous section we learned all the sum and difference formulas for sine, cosine, and tangent. We learned that cosine was antisocial and disagreeable, that sine was social and agreeable, and that tangent was just a ratio of the sums and differences. And then, of course, manipulated to have tangent in them. So what we want to show now, and one of these I kind of used ahead of time in the previous section, is the double angle formulas first and then the half angle formulas. So the way we derive these is we actually think of what is 2 times theta? Well, it's a theta plus a theta. And in the sine formula for adding two things inside the argument, we write that it would be sine of the first angle, which is theta, cosine of the second angle, which is also theta, plus, because remember sine is agreeable, cosine of theta, which is the first angle, and sine of the second angle, which is again theta. Because everything is theta, these are actually like terms, and we can add them together and get 2 sine theta cosine theta. So this is now a property or identity for us. Sine of 2 theta equals 2 times sine theta times cosine theta. For cosine of 2 theta, we would write it again as theta plus theta. And we would combine that using the formula now. So remember, cosines are antisocial and disagreeable. So cosine of the first angle, cosine of the second angle, minus, since this was a plus, sine of the first angle, sine of the second angle. That actually boils down to cosine squared theta minus sine squared theta. So cosine of 2 theta can be written this way. Because of the Pythagorean identity, we can actually manipulate this cosine in 2 different ways. So we have, remember, sine squared theta and plus cosine squared theta equals 1. That's our Pythagorean identity. So if I wanted to solve for either one of these, I would just subtract over the other piece. So for example, if I wanted to replace the cosine squared with something in terms of sine, this would be, okay, so if we have cosine squared theta minus sine squared theta, cosine squared theta is 1 minus sine squared, because you'd move that sine squared theta over in the Pythagorean identity. And notice in this case, you actually get minus sine squared theta minus sine squared theta. So you get minus 2 sine squared thetas. Now that just means that this is another or equivalent way of writing this identity. We could do something similar, but this time we could replace the sine squared with an equivalent using the Pythagorean identity. So this would still be cosine squared theta. This would be 1 minus cosine squared, because you're solving this for sine squared up here. So this would be cosine squared theta minus 1 plus cosine squared theta, because it's a negative times a negative. So this actually would give us, I'm going to write another line in here, cosine of 2 theta is actually 2 cosine squared theta, because they're both positive, minus 1. So now we have 3 ways to represent cosine of 2 theta, but only one way that we're going to use to represent sine of 2 theta. So those are our double angle formulas for sine and cosine. So let's use this. So we have, if cosine theta is negative 2/5 and theta has to be between pi and 3 pi over 2, we want to find the exact value of sine of 2 theta and cosine of 2 theta. So we know, because the sine and cosine double angle formulas are built off the sum and difference formulas essentially for sine and cosine, you need to have both sine and cosine of theta to be able to work this out. So what I'm going to first do is draw a little triangle of where this exists in the correct quadrant and label everything and try to find the third side of my triangle. So we're between pi and 3 pi over 2, which means our reference angle is right here. And this is theta. So this is negative 2 over 5, and that's cosine, which is adjacent over hypotenuse. So 2 over 5, and the 2 is the negative part, since the hypotenuse always has to be positive. So then we use our Pythagorean theorem. So y squared is going to be what I'm looking for this time. Negative 2 squared plus y squared equals 5 squared. So that's 4 plus y squared equals 25, or y squared equals 21. So y is the square root of 21, but since we're in quadrant 3, it's going to be a negative square root of 21. So then, since I have this, I can now write sine of theta in this quadrant. It would be opposite over hypotenuse, so negative square root of 21 over 5. And that does not look like a 21, it looks like a 4. Let me fix that. So 21. Okay, so let's use our formulas that we just learned. So sine of 2 theta is 2 sine theta cosine theta, which means this would be 2 times my sine theta was negative square root of 21 over 5, and my cosine of theta was given to me, negative 2/5. We have 2 times 2 on top because you can think of this as being over 1, and it's a negative times negative, so it would be positive, so that would be 4 on the square root of 21 over 5 times 5, which is 25. So there's the answer to A part. For B part, we need to do the cosine formula, and you can choose any of these. If you wanted to do, you could have done B already since you have just cosine. You could have plugged it into this version, and in fact, I think I'll do that just to show you it doesn't matter which version I pick for this case. So this would be cosine, which I already knew was negative 2/5 squared, and then minus 1. So I square that fraction first. That would make that 4 over 25. 2 times 4 is 8, so 8 over 25. Make this a common denominator by making it the same number over itself since it's a 1. And if I do 8 minus 25, that's negative 17 over 25. Now notice, if I had plugged it into this version, that would have squared the negative 2/5, and then I would have squared this, which was the negative square root of 21 over 5. That would have given me a 4 and a 21 on top, but I would be subtracting the 21 since this is minus sine squared over 25. It actually still gives you negative 17 over 25, which is what you would hope in it. With an identity, you don't want it to give you different answers. So let's come up with the tangent double angle formula. So theta plus theta for 2 theta. And remember, for tangent, you add the two angles with tangents on the top. If it's a plus already, you agree here. So this is agreeable. So it's tangent of the first angle plus tangent of the second angle over 1 minus tangent of the first angle times tangent of the second angle. The tangents on top would add together since they're like terms, so that's 2 tan theta over 1 minus tan squared theta. So there's that version. We can do even more complex things than this. For this one, this is going to take a few steps. This is 3 thetas. So we could break this down into a 2 theta and a theta. Now, because of this, we're going to have to use our addition formula for sine, because this is not just theta plus theta. It's 2 theta plus theta. Remember, for the sine formula, for addition, you are social, which means you mix your cosines and sines, and you're agreeable, so we keep this a plus. So this would be sine of the first angle, which is 2 theta, times cosine of the second angle, which is just theta, plus cosine of the first angle, which is 2 theta, times sine of the second angle, which is theta. Okay, now we have these two things that popped up, and we just figured out what these are. So now we're going to replace those. So on this next line down, this would become 2 sine theta cosine theta times the cosine theta. So this guy right here is the sine of 2 theta. Plus, you can choose any of the versions you want here. It doesn't really matter. So if you look back up here, since I think I'm going to try to keep things in terms of sine, I'm going to use the 1 minus the 2 sine squared. If you use any of the others, it eventually still works out the same. So 1 minus 2 sine squared theta times sine of theta. So this, notice, came from that. Okay, so let's simplify. This would be 2 sine theta cosine squared theta. We need to distribute this sine theta to both of those, so that would be plus a sine theta minus a 2 sine cubed theta. Okay, so at this point, if I want everything to be in terms of sine, I'm going to need to get rid of this cosine I have right here. So that guy right there. Remember, because of Pythagorean identity, that cosine squared theta can be rewritten as 1 minus sine squared theta. So that's going to be my next step. So this will be 2 sine theta parentheses 1 minus sine squared theta. So I'll highlight that to show that this is all I'm changing. Plus sine theta minus 2 sine cubed theta. Distribute the 2 sine theta out front, so this would be 2 sine theta. 2 sine theta times negative sine squared theta is negative 2 sine cubed theta. And now what I'm dealing with is like terms. These cubed ones can be added together, and the ones without the part being cubed can be added together because they're both sines to the first power. So I actually don't need this final one down here. This will be 3 sine thetas, because 2 plus 1, minus 4 sine cubed theta. So that would be sine of 3 theta written down in terms of just sines, and all of the arguments are now just thetas instead of being 3 times theta. So essentially we can use this to manipulate and make things look easier to plug into, essentially, under our calculator. Okay, this exploration right here is wanting us to use double angle formulas for cosine to help identify new identities for sine squared theta and cosine squared theta. For example, if I wanted to try to resolve this right here for sine squared theta, so I'm going to try to solve for this. First thing I would do is subtract over that 1. And then divide everything by negative 2. Now I might want to rearrange this since this is negative. That would be a positive 1 on top now and a minus cosine of 2 theta. Just rearranging it so that it looks a little nicer. So I divided everything by negative 1 essentially. And then over here this would just be sine squared theta. So this is now a new property for sine squared theta. Sine squared theta is 1 minus cosine of 2 theta divided by 2. Similarly, if we take this one right here, which is the double angle formula for cosine where it's got a cosine squared in it, I could solve this for cosine squared theta. I would add over 1, and then divide by 2. The reason this is helpful is now we can use this to talk about rewriting tangent a little differently. So we all know that tangent theta, tan squared theta is tan times tan, and a tangent is a sine theta over a cosine theta. And if you have 2 of those back to back, that makes sine squared theta over cosine squared theta. Using the properties we just discovered, the top one said sine squared theta was equal to 1 minus cosine of 2 theta over 2, and cosine squared theta is also equivalent to cosine of 2 theta plus 1 over 2. Notice that because both of these have a 2, we can multiply top and bottom by 2 and clear out those little fractions, and we just get 1 minus cosine of 2 theta over cosine of 2 theta plus 1. And this is now equivalent to tan squared theta. Now why that's helpful is because we're going to use this to now have what we call half angle formulas in just a second. So it says from this exploration that we just did, sine squared of theta is this, Cosine squared theta is this, and tan squared theta is this. Notice in all of these scenarios, this is a 2 theta over here on the right side, and the original is just a theta. That means this is half of this. So instead of just calling it theta, we call it alpha over 2, which means an angle that has been cut in half. So if we do that, we can replace these and now write 1 minus cosine of 2 times alpha over 2, because that's our theta, over 2, which makes this boil down to just cosine of alpha. So if we write it as already considering this to be a half angle, so sine squared of an angle cut in half equals 1 minus cosine of the original angle divided by 2. Similarly, cosine would look like this, which makes it cosine of alpha plus 1 over 2, cosine squared of alpha divided by 2. And tangent would be 1 minus cosine of 2 times alpha over 2 over cosine of 2 times alpha over 2 plus 1, which makes it 1 minus cosine alpha over cosine alpha plus 1. So instead of having the 2 be in all the formulas, by thinking of this just being double or this being half, you can rewrite this a little bit more simplistically. And then that leads us to the next piece, which is showing you that now we have our half angle formulas if we just take the square root of those formulas just from the last page. So when you take a square root, you don't know if the original sign was positive or negative, because remember, if you square something, a negative goes positive and a positive goes positive. So we have to write these as plus or minus, and this is a square root symbol. They don't leave enough room on this. This would be 1 minus cosine alpha over 2. The cosine half angle formula is plus or minus cosine alpha, square root of cosine alpha plus 1 over 2. And the tangent half angle formula will be plus or minus, and on the top we have 1 minus cosine alpha, on the bottom we have cosine alpha plus 1. Remember, these are all provided on that formula sheet. So let's do sine of 22.5 degrees. Now notice, if this was an alpha over 2, to find alpha, because we're going to need alpha for the formula, you multiply by 2. So this would be 45 degrees. So the sine formula says it's going to be either a plus or minus. We don't know yet. We'll determine that in just a minute. Square root. So we're questioning the plus or minus right now. This would be 1 minus cosine of 45 degrees all over 2. And this is under the radical as well. So let's plug in what we know. So cosine of 45 degrees is square root of 2 over 2. We don't like to have, and we don't know if it's plus or minus yet. We'll talk about that in a minute. We don't like to have radicals, or fractions, I should say, inside of radicals. So if we multiply the top and bottom by 2, the reason I'm choosing 2 is because that's this denominator here. This would be plus or minus 2 minus square root of 2, because I distributed that here. It cancels that 2 there, over square root of 4. And we can take the square root of 4, so we can split this into a square root on top and a square root on bottom. And so what I'm getting is square root of 2 minus square root of 2 over 2. Now, the question becomes, is this plus or minus? Well, let's look right here. To determine if something's plus or minus, you have to determine where this half angle lies. So 22.5 has its terminal side in the first quadrant, where the sine function is positive, not negative, because sine is positive in quadrant 1. So we're going to use a positive square root. So that's why we would write or think plus here. You don't physically have to write it if it's a plus. So there's that one. Okay, so let's do this cosine version. We're trying to do cosine of 5 pi over 12 using a half angle formula. So we need to figure out what would this have been if we had essentially said what is half of, if this is already cut in half, I should say. So it's already been divided by 2. So to fix that, we think of that being 2 over 1, and we multiply top and bottom by a half. Sorry, I've done that backwards. Okay, alpha over 2 equals 5 pi over 12. Okay, so we're trying to figure out what this would be. So if alpha over 2 equals 5 pi over 12, we should be able to solve for alpha. We're going to be multiplying by 2. So this would be 5 pi over 6 because the 2 and 12 reduced. So 5 pi over 6 is going to go into our formula as the original alpha before the angle got cut in half. Now I'm going to go ahead and talk about this, the quadrant thing, so I don't have to write the plus or minus the whole time. Since 5 pi over 12 is in quadrant 1, so the first quadrant, okay, the reason I know that is because 5 pi over 12 is less than pi over 2, and that's, remember, the end of quadrant 1 essentially, because this, if you put it in a common denominator, is 6 pi over 12. So 5 pi is less. So that means in quad 1, cosine is positive. You do have to care about what your trig function is, because if we were in quad 2, cosine would be negative, and we'd have to make our angle then negative. And then the square root is going to be positive still. Okay, so this will be square root of, and remember for the cosine half angle formula, it's cosine of the alpha, which is 5 pi over 6, remember, plus 1 over 2. So we need to think about where 5 pi over 6 is. So remember, this is the angle before it got cut in half. 5 pi over 6 is over here, and it is a 30-degree reference angle, so this is 1 square root of 3 and 2, where this is negative. So cosine of that is negative square root of 3 over 2. Plus 1 over 2. Again, I'm going to multiply top and bottom by 2 to clear out that little fraction. So this would be negative square root of 3 plus 1, or plus 2, sorry, because I'm distributing that over 4, and that's under a square root as well, and we can take the square root of 4. Now, if you want, you could rewrite the top. A lot of people don't like the negative to come first, so 2 minus the square root of 3 over 2. So square root of 2 minus the square root of 3 over 2. And again, if they ask for an exact value, you don't want to go to a decimal. You want to leave it like that. Okay, example 4. We're going to look at this half angle formula a little bit differently. If we said that tangent of alpha was negative 1/5, and we know that alpha is in quadrant 2, between pi over 2 and pi, find the exact value of sine of alpha over 2. The problem with this is we are not starting out with what our half angle is. Our ratio that we were given is based on the original alpha, not the alpha over 2. So you do need to figure out what quadrant things are going to be in. First of all, the original angle, the one before it got cut in half, is in quad 2. How do you know what quadrant alpha over 2 would be in? You take this little inequality that they've given you, and you just multiply everything by 1/2. You take half of everything, essentially. That would make this pi over 4 is less than alpha over 2 is less than pi over 2. So if you just divide each of the 3 pieces given here by 2, or essentially you multiply by a half, that will tell you where alpha over 2 is. It's between pi over 4 and pi over 2, which are both in quadrant 1. So this is going to be in quadrant 1. Our final answer is supposed to be to find a sine value, and in quadrant 1, sine is positive. Okay, so then let's work it out. So the first thing I would probably do is draw a picture of the original angle I was given, which was alpha was over here, and we knew that tangent of alpha was negative 1/5, because that's essentially all I know except for where the half angle ends up, which is in quadrant 1. So this is opposite over adjacent, so that would be 1 over 5, and the negative goes with the x-axis over here. So we use Pythagorean theorem to find our hypotenuse. So this would be 1 plus 25 equals c squared. 26 equals c squared, so square root of 26 equals c. And it's positive since it's the hypotenuse. Okay, so now that we know that cosine of alpha, because remember all of our formulas are using cosine when we do the half angle formulas, is negative 5 over the square root of 26. We'll probably want to rationalize that. So that'd be negative 5 square root of 26 over 26. Okay, so let's plug in what we know. So sine of alpha over 2 is square root, and it's positive since of what quadrant we were in, and we checked what the sign is in that quadrant. This would be 1 minus negative 5 square root of 26 over 26 all over 2. Okay, so that's minus a negative, so that's going to be plus. Again, I don't like having a little fraction on top, so I'm going to multiply everything on top and bottom this time by 26, because that's my denominator. So this will be square root of 26 plus let's see, that will be, the 26 are going to cancel in the second part. 5 times the square root of 26 all over the square root of, this is 52 now. This is 2 times 26. All right, so we have a couple problems here. The top is actually okay the way it is right now, but we can't leave this down here because it's a square root. So the first thing you could notice is that this does break down into a perfect square and a non-perfect square. So if I wanted to simplify that first, least would make the radical part on the bottom smaller. That would be a 2 on the square root of 13. So to get rid of this radical, I need to multiply top and bottom by the square root of 13. Now, this is where most people would make a mistake about multiplying. When you multiply two radicals together, especially if there's another radical inside, you can only multiply numbers together if they're under the same number of radicals. So 13 is under the same number of radicals as this 26 and this 5, so it can be multiplied times both of those. Sometimes they won't make you write that out. They'll just be like, just do 13 times this, and that's acceptable. Just depends on the homework feature or the book. This would be 2 times now 13. So if we leave it like that, just in distributed form on top, so that we don't have to multiply all that out, this would now be 26 in the denominator. So a pretty messy answer for this one. Okay, and lastly, there are two alternate formulas for the half-angle formula for tangent. One is 1 minus cosine alpha over sine alpha. The other is sine alpha over 1 plus cosine alpha. We went through great detail on a lot of the formulas about how they've derived them, so we're not going to do that on this one. Most people use just the traditional half-angle formulas, but these are nice because they don't have the square root. Therefore, the sine part for tangent is already figured out. So they are worthy in that regard. Okay, that is the end of the 8.6 notes.